For millennia, humanity gazed at the night sky, believing that what our eyes perceived was the entirety of the cosmos. Our cosmic understanding was limited to the visible light that reached us, painting a picture of stars, planets, and galaxies as shimmering points against an inky black canvas. Yet beneath this familiar spectacle lay a universe far richer, profoundly more complex, and largely hidden from our direct senses. This unseen realm, teeming with data we couldn't detect, held profound secrets about the universe's origins, its evolution, and its ultimate fate. It was a universe of invisible energies, exotic particles, and subtle forces, constantly interacting, shaping the very fabric of space and time. Our challenge was to transcend our biological limitations and develop new senses. The journey to unveil this hidden cosmos began not with a single breakthrough, but with a series of incremental discoveries pushing the boundaries of what was observable. Each technological leap, from refined telescopes to sophisticated detectors, chipped away at the veil, revealing new layers of cosmic truth. It was a quest driven by insatiable curiosity and relentless scientific inquiry. We discovered that the light we see, the visible spectrum, is merely a tiny sliver of a much grander phenomenon, the electromagnetic spectrum. Beyond red lies infrared, microwaves, and radio waves. Beyond violet lies ultraviolet, X-rays, and gamma rays. Each band carried unique information, telling a different story about cosmic events and objects that visible light alone could not reveal. Radio astronomy, born from the accidental detection of cosmic signals, became one of the first windows into this unseen universe. Karl Jansky's pioneering work in the 1930s, while studying static interference, inadvertently stumbled upon radio waves originating from the center of our Milky Way galaxy. This unassuming discovery marked the dawn of a new era. Jansky's findings, initially met with skepticism, proved that celestial bodies emitted more than just visible light. They emitted powerful radio waves, signals that could penetrate cosmic dust clouds, allowing us to see through obscurities that rendered visible light observations impossible. This breakthrough fundamentally reshaped our approach to cosmic exploration. The subsequent development of dedicated radio telescopes, massive dishes designed to collect these faint signals, revolutionized our understanding of galactic structures, quasars, and pulsars. These colossal instruments, often spread across vast distances to synthesize a single giant ear, allowed us to map the universe in unprecedented detail. One of the most monumental discoveries in radio astronomy came in 1964, a serendipitous finding by Arno Penzias and Robert Wilson. While calibrating a new horn antenna, they detected persistent, inexplicable background noise, uniform in all directions. It was initially dismissed as pigeon droppings, a testament to scientific humility and perseverance. This pervasive static, the cosmic microwave background radiation, was soon identified as the afterglow of the Big Bang itself. It was the universe's earliest light, stretched and cooled over billions of years into microwave wavelengths. Its discovery provided compelling evidence for the Big Bang theory, transforming cosmology from speculation to observable science. The cosmic microwave background provided a snapshot of the universe when it was merely 380,000 years old, a time before stars and galaxies had formed. Its faint temperature fluctuations, mere millionths of a degree, were the seeds from which all cosmic structures, galaxies, clusters, and superclusters would eventually grow, offering an unparalleled glimpse into cosmic infancy. While radio waves unveiled the very large-scale structure and ancient echoes, infrared astronomy opened a window into the universe's cool and dusty regions. Much of the cosmos is obscured by vast clouds of gas and dust, opaque to visible light, where stars and planets are born. Infrared radiation, however, can penetrate these nebulae. Warm objects, even those too cool to emit visible light, radiate in the infrared spectrum. This includes forming stars nestled deep within their stellar nurseries, dusty protoplanetary disks swirling around young suns, and the cooler parts of distant galaxies. Infrared telescopes act like thermal cameras for the universe. Early infrared observations were largely ground-based, but atmospheric water vapor significantly absorbs infrared light, limiting observations. This challenge spurred the development of airborne and then space-based infrared observatories, elevating our cosmic vision beyond Earth's obscuring veil. The Infrared Astronomical Satellite, IRAS, launched in 1983, was a landmark mission. It conducted the first all-sky infrared survey, detecting hundreds of thousands of previously unknown infrared sources, including new galaxies, forming stars, and dusty disks around other stars, suggesting the presence of nascent planetary systems. Following IRAS, more sensitive infrared telescopes like the Spitzer Space Telescope, launched in 2003, offered unprecedented clarity. Spitzer, observing in 4 infrared wavelengths, offered breathtaking images of star formation regions, galactic cores, and the atmospheric compositions of exoplanets as they transited their host stars. The James Webb Space Telescope, a marvel of modern engineering, has further pushed the boundaries of infrared astronomy. Its primary mirror, nearly 6.5 meters in diameter, allows it to detect the faint infrared light from the most distant, earliest galaxies in the universe, whose visible light has been stretched into infrared by cosmic expansion. Webb's ability to see through cosmic dust and peer back in time to the universe's infancy provides critical data on the formation of the first stars and galaxies. It's revealing that these early galaxies were surprisingly mature and massive, challenging existing cosmological models and prompting new theoretical considerations. Moving further up the electromagnetic spectrum, ultraviolet astronomy explores the hottest and most energetic phenomena. Hot, young stars, superheated gas, and the energetic death throes of massive stars emit profusely in ultraviolet. Earth's atmosphere, however, heavily absorbs most UV radiation. Just as with infrared, the solution for observing ultraviolet light lay beyond Earth's protective atmosphere. Orbital observatories, free from atmospheric absorption, became crucial. Early-sounding rockets carried small UV instruments, providing fleeting glimpses of the UV sky before plunging back to Earth. The International Ultraviolet Explorer, IUE, launched in 1978, was a collaborative success, operating for an unprecedented 18 years. It provided spectroscopic data on countless celestial objects, from comets in our solar system to distant quasars, revolutionizing our understanding of galactic halos and supernovas. The Hubble Space Telescope, while famed for its visible light images, also possesses powerful ultraviolet observational capabilities. Hubble has used its UV sensors to study phenomena like starburst galaxies, the energetic jets from active galactic nuclei, and the compositions of exoplanet atmospheres for signs of life. Ultraviolet data is essential for understanding the processes that shape galaxies, particularly the cosmic web of gas that connects them. It allows astronomers to study the conditions of extreme environments where atoms are stripped of their electrons, revealing dynamic and energetic processes otherwise invisible. Advancing further still, X-ray astronomy probes the most violent and energetic events in the universe. Black holes devouring matter, superheated gas in galaxy clusters, and the fiery remnants of supernova explosions emit intense X-rays, charting processes that generate temperatures millions of degrees Kelvin. X-rays are completely absorbed by Earth's atmosphere, making space-based observatories absolutely essential. Early rocket flights detected X-rays from the Sun, but the discovery of Scorpius X-1 in 1962, the first cosmic X-ray source beyond our solar system, truly marked the birth of X-ray astronomy. The Chandra X-ray Observatory, launched in 1999, stands as a testament to this field. With its incredibly sharp X-ray vision, Chandra has revealed the distribution of dark matter in galaxy clusters, detected echoes of supernova explosions, and studied the environments around black holes with unprecedented detail. X-ray data provides crucial insights into galaxy cluster dynamics. The superheated gas, millions of degrees hot, that pervades these clusters emits X-rays, allowing astronomers to map their total mass and understand how they grow through mergers. This gas also acts as a tracer for the distribution of dark matter. Furthermore, X-ray observations are vital for understanding the extreme physics around black holes. As matter spirals into a black hole, it heats up to millions of degrees, emitting a torrent of X-rays before it crosses the event horizon. This allows us to study the accretion disks and powerful jets emanating from these cosmic behemoths. At the highest energy end of the electromagnetic spectrum lie gamma rays, emitted by the most cataclysmic events in the universe. Gamma ray bursts, the hypernova of massive stars, and the interaction of cosmic rays with interstellar gas all produce these incredibly energetic photons. These are the beacons of cosmic violence. Like X-rays, gamma rays are absorbed by Earth's atmosphere, necessitating space-based detectors. The Compton Gamma Ray Observatory, launched in 1991, was a major stepping stone, revolutionizing our understanding of gamma ray bursts as distinct, powerful, and mysterious cosmic events. The Fermi Gamma Ray Space Telescope, launched in 2008, continues this legacy, mapping the gamma ray sky with unprecedented sensitivity. It tracks cosmic accelerators, sources of powerful gamma rays within pulsars and active galaxies. Its data helps us understand the extreme conditions where particles are boosted to near light speed. While the electromagnetic spectrum has vastly expanded our cosmic view, some of the universe's most profound secrets lie in phenomena that aren't light at all. Neutrinos, often called ghost particles, are one such example. They are incredibly small, nearly massless, and interact very rarely with matter, allowing them to traverse vast cosmic distances unimpeded. Billions of neutrinos stream through our bodies every second, primarily from the sun, without us ever feeling them. Their elusiveness, while challenging for detection, is precisely what makes them invaluable. They carry pristine information directly from cosmic events that are otherwise opaque, like the sun's core or supernova explosions. Early theories of the sun's energy production, based on nuclear fusion, predicted a specific flux of neutrinos. However, initial experiments in the 1960s, notably the Homestake experiment, detected fewer solar neutrinos than expected, leading to the solar neutrino problem, a major puzzle for astrophysics. This deficit of solar neutrinos was eventually explained by the phenomenon of neutrino oscillation, where neutrinos change their flavor or type as they travel from the sun to Earth. This groundbreaking discovery proved that neutrinos possess mass, a significant departure from the standard model of particle physics and a Nobel Prize-winning insight. Beyond the sun, neutrinos offer a unique window into supernova explosions. When a massive star collapses, it releases an immense burst of neutrinos milliseconds before the light from the explosion reaches us. Detecting these neutrinos provides an early warning and direct information about the chaotic core of a dying star. The Superkamiokan detector in Japan, a massive tank of ultrapure water buried deep underground, is a prime example of a neutrino observatory. When a neutrino rarely interacts with an atomic nucleus in the water, it produces a tiny flash of light, called Cherenkov radiation, which sensitive photodetectors can record. IceCube, a neutrino observatory at the South Pole, takes this concept to an even larger scale. Thousands of sensors are embedded deep within a cubic kilometer of Antarctic ice, patiently awaiting the telltale flashes of light from high-energy cosmic neutrinos interacting with the ice. IceCube has detected neutrinos from beyond our galaxy, tracing them back to active galactic nuclei and blazars, confirming these as powerful cosmic accelerators. These high-energy neutrinos offer a new way to map the extreme cosmos, pointing to sources of cosmic rays that would otherwise remain masked. Another enigmatic form of unseen data comes from cosmic rays, high-energy particles, mostly protons and atomic nuclei, that constantly bombard Earth from outer space. Discovered in the early 20th century, their origin and acceleration mechanisms have been a long-standing mystery. Early cosmic ray detectors used balloons to ascend into the atmosphere, as the atmosphere itself absorbs and breaks down these energetic particles into showers of secondary particles before they reach the ground. These pioneering flights offered the first insights into the energy and composition of cosmic rays. While low-energy cosmic rays primarily originate from our Sun, ultra-high-energy cosmic rays, possessing energies far exceeding what man-made accelerators can achieve, come from truly exotic and violent events far beyond our galaxy. Their origins are a major area of ongoing research. The Pia Auger Observatory in Argentina is the world's largest experiment dedicated to detecting ultra-high-energy cosmic rays. It uses a vast array of water-Cherenkov detectors spread over 3,000 square kilometers, along with fluorescence telescopes, to observe the air showers produced by these incoming particles. Because cosmic rays are charged particles, their paths are bent by galactic and intergalactic magnetic fields. This makes it difficult to trace them back to their source, similar to trying to find the origin of a cannonball after it has ricocheted off countless unpredictable surfaces. However, at energies exceeding a certain threshold, cosmic rays are less affected by magnetic fields, making direct astronomical identification of their sources more plausible. This threshold, known as the Greisen-Zatze-Pinkuzman limit, or GZK limit, predicts interactions with the cosmic microwave background. Data from cosmic rays helps to understand extreme astrophysical accelerators like supernova remnants, pulsars, and active galactic nuclei. These powerful cosmic engines act as natural particle accelerators, boosting particles to incredible speeds and energies far beyond human capability. Even more elusive than neutrinos and cosmic rays are gravitational waves. Predicted by Einstein's theory of general relativity over a century ago, these ripples in the fabric of spacetime, created by accelerating massive objects, are incredibly faint and challenging to detect directly. Imagine stretching and squeezing space itself. That's what a gravitational wave does. As it passes, it momentarily distorts distances between objects. These distortions are infinitesimally small, making their detection a monumental feat of engineering, requiring exquisite precision. The first direct detection of gravitational waves occurred in 2015, a century after Einstein's prediction, by the Laser Interferometer Gravitational Wave Observatory, or LIGO. This historic observation from the merger of two black holes opened an entirely new window onto the universe. LIGO consists of two identical detectors, thousands of kilometers apart, in Livingston, Louisiana, and Hanford, Washington. By detecting a gravitational wave event almost simultaneously at both locations, scientists can confirm the signal's cosmic origin and rule out local disturbances. The signal detected by LIGO was a characteristic chirp, the sound of two massive black holes spiraling inward and merging into a single, even larger black hole, releasing an enormous amount of energy in the form of gravitational waves. This event was a direct confirmation of black hole binaries. This groundbreaking discovery ushered in the era of gravitational wave astronomy, allowing us to observe phenomena that are electromagnetically silent. Black holes, by definition, do not emit light, but their powerful gravitational interactions create detectable ripples in spacetime. A monumental event occurred in 2017, the first detection of gravitational waves from the merger of two neutron stars. Unlike black hole mergers, neutron star mergers produce not only gravitational waves, but also a massive burst of electromagnetic radiation across multiple wavelengths. This simultaneous detection, known as multi-messenger astronomy, combined gravitational wave data with observations from telescopes worldwide. It provided irrefutable proof that neutron star mergers are the primary cosmic factories for producing heavy elements like gold and platinum, forged in these cataclysmic events. Future gravitational wave observatories, like LISA, Laser Interferometer Space Antenna, will operate in space, listening for low-frequency gravitational waves from supermassive black hole mergers at the centers of distant galaxies. These instruments promise even deeper insights into the evolution of cosmic structures. Beyond direct detections, much of our cosmic understanding relies on indirect evidence and inferred data, especially concerning the universe's most mysterious components, dark matter and dark energy. These constituents represent about 95% of the universe's total mass energy, yet remain entirely unseen. The concept of dark matter arose from observations in the 1930s by Fritz Zwicky, who noted that galaxies within the Coma cluster were moving far too fast to be held together by the visible matter alone, suggesting a significant amount of unseen mass. His initial observations, though groundbreaking, were largely overlooked. Decades later, in the 1970s, Vera Rubin and her colleagues provided compelling evidence for dark matter by studying the rotation curves of spiral galaxies. They found that stars at the outer edges of galaxies were orbiting at unexpectedly high speeds, implying a halo of invisible mass extending far beyond the visible disk. Without this additional, unseen gravitational pull, these galaxies would simply fly apart. Dark matter, therefore, provides the cosmic scaffolding upon which galaxies and galaxy clusters are built. It's the glue that holds large-scale structures together, shaping the cosmic web. Numerous experiments worldwide are actively searching for dark matter particles, hoping to directly detect their rare interactions with ordinary matter. These experiments are often conducted deep underground to shield them from cosmic rays and other background interference. Candidates for dark matter include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Each candidate presents unique detection challenges, but the pursuit of direct evidence for dark matter continues to be one of the most exciting frontiers in physics. If dark matter explains why galaxies don't fly apart, dark energy explains why the universe's expansion is accelerating. This even more enigmatic component constitutes about 68% of the total mass energy of the observable universe, dominating its fate. The accelerating expansion was discovered in the late 1990s by two independent teams studying Type Ia supernovae. These standard candles have a known intrinsic brightness, allowing astronomers to measure their distances accurately. The more distant a supernova, the more its light is redshifted due to cosmic expansion. The supernova data unexpectedly showed that distant supernovae were fainter than predicted, implying that they were further away than their redshift alone suggested. This could only mean that the expansion of the universe was speeding up, not slowing down as expected from gravity's pull. This discovery of cosmic acceleration won the Nobel Prize in Physics in 2011 and launched the era of precision cosmology. It forced a dramatic re-evaluation of our most fundamental theories about the universe, suggesting a mysterious anti-gravitational force at play on cosmic scales. The nature of dark energy remains one of the greatest unsolved mysteries in science. Is it a cosmological constant, as Einstein once theorized, a pervasive energy inherent to space itself? Or is it a dynamic, evolving field, shifting over cosmic time? Experiments like the Dark Energy Survey and upcoming missions like Euclid and the Nancy Grace Roman Space Telescope are meticulously mapping billions of galaxies to understand the growth of large-scale structures and probe the influence of dark energy over cosmic history. The interplay between dark matter, which pulls structures together, and dark energy, which pushes them apart, dictates the ultimate fate of the universe. Current data suggests an ever-accelerating expansion, leading to a big freeze, where galaxies eventually drift so far apart that the universe becomes cold, dark, and empty. Unseen data isn't just about discovery, it's also about interpretation and processing. The sheer volume of information collected by modern observatories poses an immense challenge. Terabytes and petabytes of data stream in daily, far exceeding human capacity for manual examination. This is where artificial intelligence and machine learning become indispensable. AI algorithms can sift through vast datasets, identify subtle patterns, classify galaxies, detect gravitational wave signals, or even discover exoplanets far more efficiently and precisely than human counterparts. Machine learning models are trained on existing cosmic datasets, learning to distinguish between cosmic phenomena and terrestrial noise, or infer properties of objects like black hole masses from faint signals. This accelerates the pace of discovery, turning raw data into scientific insights. Beyond data processing, simulations play a crucial role in understanding the unseen universe. Cosmological simulations, powered by supercomputers, recreate the universe's evolution from the Big Bang to the present, incorporating the effects of dark matter and dark energy. These simulations generate synthetic observational data that can be compared with real-world observations, helping to refine our cosmological models and test theories about the nature of dark matter and dark energy. They fill in the gaps where direct observation is impossible. The future of exploring unseen data promises even more audacious projects. Next-generation telescopes, both ground-based and in space, will push the limits of sensitivity and resolution across the electromagnetic spectrum, unveiling fainter and more distant cosmic secrets. New gravitational wave detectors, like the Einstein Telescope in Europe and Cosmic Explorer in the US, will be even more sensitive than LIGO, potentially detecting gravitational waves from the very early universe, just moments after the Big Bang. The search for dark matter continues with innovative approaches, including direct detection experiments with improved shielding and sensitivity, as well as indirect searches looking for the annihilation products of dark matter particles in space. Quantum sensors, leveraging the principles of quantum mechanics, are emerging as a powerful new tool in highly sensitive measurements. They could one day detect ultra-faint gravitational waves or even subtle interactions with dark matter particles, pushing the boundaries of what is detectable. The pursuit of unseen data constantly challenging our assumptions. The very existence of dark matter and dark energy suggests that our current standard model of particle physics and general relativity, while incredibly successful, is incomplete. They point towards a deeper, perhaps more complex, underlying reality to the universe. Could there be extra dimensions, new forces? The unseen data pushes us towards a paradigm shift, prompting new theoretical frameworks to encompass these enigmatic cosmic constituents. The data has profoundly shaped our cosmic worldview. We've moved from a universe of visible stars to a dynamic, expanding cosmos dominated by dark, invisible components, born from a singular event and governed by forces still poorly understood. It has instilled in us a profound sense of humility, recognizing how little we truly knew, and an even greater sense of wonder at the universe's boundless secrets. Our quest to perceive the unperceivable is a testament to the insatiable human desire to comprehend our place in the grand tapestry of existence.